weird than waiting 5 minutes to say, are you, so don't be shy to speak up. But the foundation of physics and engineering, and I would even say the technology, the foundations of the physical world are motion, force, work, and energy. Everything is sort of built upon these fundamental categories. And you could argue, well, really, these are all a single category. But for now, we'll just leave it at these four categories. Motion was chapters 2 and chapter 4. Chapter 2 was one-dimensional kinematics. Chapter 4 was two-dimensional kinematics. Force was chapters 5 and 6. The only difference between chapter 5 and 6 is chapter 6 includes centripetal motion and friction. Work was chapter 7. Energy is still kind of chapter 7 and chapter 8. So that's what I'm saying. Chapter 8 is the end of the beginning, because going forward, everything we do kind of is just a remixing of these four basic categories. So chapter 8 is in many ways like the pinnacle. Chapter 8 is all about, I think it says potential energy, and conservation of energy. Potential energy and conservation of energy. So here's our first problem. You're skiing down a ski slope. This is you. You decide to go skiing. This is you on the slope. You go speeding down the slope, and then you go off this ramp. The question is, how high do you get? So the question mark here is, if this is the situation, what's that? How high above? It says, what is the maximum height, little h, of his jump above the end of the ramp? So this is what we're looking for right here. We're looking for that little h value. So I'm going to introduce the third of the three great methodologies. We started with the kinematics analysis method, with the force analysis method, and now we get to the energy analysis method, which to me is the simplest and yet most useful of all three methodologies. The energy analysis method, I actually think, is the most efficient. And you can tell me if you disagree, but here are the recipe items. Number one, ID energy state. So, and this is in your green sheets. I'm just kind of going through all these basic categories right now, but it's a methodology, which just means a series of recipe steps. So recipe step number one is let's ID energy states. ID energy states. So this is sort of situational. You have to kind of get a little bit of practice. It's pretty straightforward. ID energy states. So when I look at this system that's described for us in this problem, I can't help but think of this maybe as this is an energy state, the skier at the very top of the ramp. That seems like a natural label. This right here seems like another natural label, the skier at the bottom of the ramp, right at takeoff. So I'm going to call that energy state B. And this seems like yet another natural energy state, the skier at the very top of this trajectory. So I'll call that energy state C. And there might be more. And this will be, it's always the case. This is my first draft. If I have to adjust this, I will. But you got to start somewhere. This is draft number one of my energy states. Here's another recipe item. Establish a baseline. Establish a baseline. And this is totally up to you. It's like, this is sort of like establish a coordinate system. So here's what I'm going to call a baseline. Baseline is my reference point. This is my baseline. And I guess I'm calling that point baseline. So I've done that. I'm going to call this is my baseline, and really subscripting everything is so helpful. This is my baseline. This is where H H subscript B equals 0. H subscript B is the right here. This is the height. This is the height at B. So H subscript B is referring to the height at this point. If H subscript B is 0, then that means the following. It means the gravitational potential energy at B, which equals mgHb, that also equals 0. So you can see this baseline's a big deal. Again, it's like a coordinate system. It's like being smart about how to set up your coordinate system. Same here. You need to be thoughtful about this. And then I want to talk about the green sheets, which again, this to me, I think is it's an essential practice. If you guys can just always get in the habit, meaning no exceptions, if you can always be in the habit of checking out that YouTube green sheet lecture video before class, not after. After can happen multiple, that can be like your second time. But if you can give this at least an initial digestion before this class, what you're about to be exposed to is going to be much more meaningful. So if you didn't watch the lecture video again, I have no way of knowing. I'm just saying I am interested in you doing better on exams, and this is a way to do better on exams. This is in this section right here. This is the part of your lecture notes described in uncompromising detail in these lecture videos. So you're gonna learn it. You're gonna learn it. You won't have any gaps in the backstory here. It's going to be described in great detail, and it is here on the screen. Although there's a difference between looking at steps 6, 7, 8, 9, and 10 versus looking at those steps and having somebody narrate that through, provide a narration, which the green sheet lecture videos do that. So this is what I'm keying on here. This is gravitational potential energy. And even up here, it said, what is potential energy? And it talked about what is potential energy. It's the energy of position or configuration. And then it gives you some examples. So I don't want to repeat the green sheet lecture video now, other than maybe an occasional reference or two, but it's there. It's there. You're going to learn so much from that, especially if you have watched it before, not after. All right. So just yet another reminder. Let's go ahead and keep going here. ID the energy states done. I drew my baseline done. And then part C is apply EAM equation. Apply EAM equation. So it's kind of it. I mean, there's some more details here, but this is in essence this methodology. There's my baseline. I'm sorry. I ID my energy states A, B, and C. Maybe I'll have to update, maybe not. But A, B, and C look like natural points to label. The skier at the top of the ramp, just taking off the ramp, and maybe at the very peak. You could argue, I could see how you might say, well, maybe shouldn't I put a baseline here? An ID there. Maybe, maybe not. Maybe I'll have to do that. But I'm done with identifying the energy states. I established my baseline. And now I'm ready to do conservation of energy, which is right here, ready. This is the EAM equation. It says the following: whatever energy, what should I do between? I'm going to do between A and C. Whatever energy I have at state A plus whatever non-conservative work occurs equals my energy at state C. This is conservation of energy. So what it's saying, the way I drew it, consider the skier's total energy here at energy state A. Whatever that total amount of energy is, it's going to be the same as it is here at state B minus some non-conservative work. So a quick sidebar about an essential subtopic here called non-conservative work. WNC means non-conservative work. And I think the example I used in the lecture video, which I will briefly repeat here, not non-conservative, or I will briefly repeat here. But imagine that I'm walking along the floor. So there's the floor. Here's me walking. This is me walking on the floor like that. And I'm walking from point A to point B. So I'm walking along a carpet, just even better, a carpeted floor. So there I am at point A. Here I am at point B. And this is my displacement. I walked from point A to point B. And every step of the way, I was sliding my feet. I was purposely dragging my shoes to create as much friction as possible. Okay, so I walk from point A to point B. Now, when I walk from point A to point B, friction force is doing work because, again, I'm scraping my feet along the carpet. What if I went from the same point A to the same point B, but instead of going in that straight line, what if I started out? What if I started out at point A, just like I am here, but I turn around and I back step and then I stop and then I go forward and then I back up again. And then, so I basically kind of meander. I kind of just sort of go on some random circuitous path from point A to point B. The work done by friction, the work done by the kinetic friction force is going to be, for the orange, is going to be greater than the work done due to the friction force for the purple. And that's because kinetic friction is a non-conservative force. F sub k is a non-conservative force. What does that mean? A non-conservative force is path dependent. So F sub k is a non-conservative force. The work done by a non-conservative force, in this case F sub k, depends on path. Like you can see here. So again, look at the difference. Appreciate the difference you're seeing between this orange path and the red path. And I should have said red. So let me change this to red. This should have been the work done by the friction force along that red path. This red path, this was the direct straight line path. So this is true. The work done via the orange path is greater than the work done along the red path. That's because friction depends on path. The longer the path, the more work gets dissipated. What's not a friction force? A lot of things are not. I'm sorry. What is a conservative force? Here's the ground. So imagine this is just a tabletop. And you take a ball, a purple ball, and this purple ball is lifted from point A to point B. This might be point A. This might be point B. Gravity does a certain amount of work on that purple ball. As it moves from point A to point B, gravity is doing some amount of work. What if instead of going directly from point A to point B, this purple ball follows this path? It goes from point A, but then it stops here, turns around, maybe goes over here for a few meters, and then goes. So what if this purple ball followed this very erratic path, but still ended up at that same point B? So I'll do it like this. Just this weird random path, but still ended up at that same point B. In this case, the work done by that gravitational force along that brown path is actually completely equal to the work done by the gravitational force as it goes along that green path. So that's what it means to be a conservative force. Conservative force path doesn't matter. The only things that matter are the end states. Where did you start off from and where did you end up at? So that's the big difference between a conservative force and a non-conservative force. So that's a big deal, which is why I'm spending lots of time on it. Okay. So having said that, back to the solution. Step 2. What kinds of energy does this skier have at point A? Well, the skier could have some kinetic energy. So let's record it. The skier could have some gravitational potential energy. Non-conservative work. And the thing I'll start mentioning, non-conservative work can actually add or subtract. Non-conservative work can add energy to the system or steal energy for the system. At energy state C, I might have some kinetic energy at C. I could have some gravitational potential energy at C. So let's just keep developing this. This is just conservation of energy. All right. What is kinetic energy? 1/2 mVA squared. Stay committed to subscripts. Otherwise, you'll get lost, and equally bad, I'll get lost when I grade your work. And the reader, you have to make the graders work easy. And by grader, I mean your instructor or your boss or a customer or a colleague. You have to present work that's really easy to follow. So that's kinetic energy at A. Here's gravitational potential energy at state A, mgha. Gravity only cares about position with respect to a baseline, and that's what I have. Non-conservative work. So you would read this basically. This term, non-conservative work, is the amount of work that happens from A to B, or in this case, A to C, because I'm going from A to C. I'm skipping B. All right. So again, this is non-conservative work that happens occurring between A and C. Occurring between energy state A and energy state C, because I get to select any two energy states. The energy is going to be conserved between energy state A and C. Number 4, let's talk about low-hanging fruit. Low-hanging fruit means let's deal with the obvious right now. Low-hanging fruit means you just reach up and you take care of you pick the lowest hanging apples from the tree without any effort. But I'm not even done here. Plus WNC, okay, equals 1/2 mv subscript C squared plus mghc. And there's my dollar sign. So good news. I've identified my dollar sign. How high does this skier get above the baseline? So the selection of the baseline was easy. They kind of led my way. So now we talk about, after you do this initial setup of the EAM equation, let's talk about the low-hanging fruit. The skier is starting from rest. So you know what? There. This whole term equals 0. Starts from rest because of the description. Starts from rest. The skier is starting from rest at a height of, this is what I'm calling HA. HA is given. HA is 22 meters. Other low-hanging fruit. Yeah, here's some right here. I'm at C, huh? No, there's no more low-hanging fruit there. Here's the only other piece of low-hanging fruit. Ready, set, go. WNC equals 0 because no mention of energy givers or taker. No mention of any external forces doing non-conservative work. And again, an external force could add energy. What's a way of adding energy? Let's say, for example, you're skiing down this ramp. And as you ski down this ramp, you're wearing a jetpack. And this jetpack basically is providing a whole bunch of propulsion and is like a jet engine that you're wearing on your back. And this would be an example of a non-conservative force that's actually adding energy to the system. But there's no jetpack, there's no air resistance, there's no friction, there's no tow ropes. A tow rope could add energy or take away energy, but there's no mention of energy stealers or energy givers, energy givers or takers. Okay, so here's our new. We graduate from step 3 to step 5. All right, so ready. Oh no, I don't. That's equal to 0. So MGHA. Oh, there's one other piece of low-hanging fruit. I can cancel M's everywhere. So this mass cancels with with this mass cancels with that mass. All right, so that is some low-hanging fruit because that's an easy simplification to make. So here's where I am now in terms of my energy balance. All right, ready? I have GHA. I know G, I know H subscript A equals 1/2 VC squared plus GHC. And there's my $sign. And this, again, looks quite a bit easier. This is my $sign. All right, so let's see. I know G, I know H sub A, so feeling good. I know G, I know H sub A, it's given. Mine's 22. Here's the problem. So here's an uh-oh. What's V sub C? What's my launch velocity? So this is a big let me draw my, this is V sub C. That's not my launch velocity, it's my velocity at C. Here's my velocity at C. When this skier is at point C, ready, set, go. This is the velocity. So this is V sub C. V sub C is purely X velocity at point C. Vy equals 0. Vy equals 0 because I'm at the very top of this trajectory. This is two-dimensional projectile motion. It should look pretty familiar to you. Okay, so all I need to do is find V subscript C, also known as V subscript X. I think I can do that because here's my launch velocity. I'm going to just draw this vector a little bit easier to read. Here's my launch velocity right here. Just making it a little bit bigger. All right, let's do the components thing. It's a two-dimensional vector. Here's the X component. Yes, here's the Y component. Let's label this. This is VB. Okay. This is VBX. And right here, this is VBY. So, I better update this a little bit because the velocity at C is the same as VBX. I'm going to just modify this. So a little bit of an update. I think this is better because there's no acceleration in the X dimension. So again, this is pure review. You should totally understand why this velocity right here, VBX, is completely the same as VC. Okay, because A sub X equals 0. All right, so I think we can use that. let's go back. Let's keep going. Number 6. Number 6. VBX equals VB cos theta. Okay. And you know what? That is the same as VC. And let's just do a little trig sidebar here. The trig sidebar that spits that out says, well, okay, for this triangle, cosine of theta, referring to this triangle right below, is side adjacent, which is VBX, all over the hypotenuse, which is VB. And that's why I'm saying VBX equals VB cos theta. But wait, there's another fly in the ointment. What's VBX? Or what's VB? Sorry, I know theta. What's VB? Question mark. Okay, the answer is I don't know. So I'm going to do this. I'm going to do another EAM. And this is a standard. You know by now you're always going to be running into dead ends, and you have enough practice so that you know you're going to be pretty darn capable of getting out of these dead ends, because that's what practice is for. All right, so number 8, EAM to the rescue. Let's do energy at state A plus non-conservative work equals energy at state B. So I am going to look at this energy between A and B, because I need to get VB. That's my motivation. And just doing this out in like painfully small baby steps, just to make sure nothing's left uncertain. At energy state A, which is right here, energy state A, maybe there's some kinetic energy, but there's not. I'm starting from rest. Maybe there's some gravitational potential energy. Maybe there's some non-conservative work. In this case, there's not. Nothing is adding or stealing energy. And then same thing at B. Account for possible kinetic energy, account for possible potential energy. And I'll do the low-hanging fruit right now, because I'm starting from rest, which means 1/2 mVA squared equals 0, because I'm starting from rest. This is equal to 0 for the aforementioned reason. There's no description of non-conservative forces. This is equal to 0. This is my baseline. So there's a lot of simplification that just happened. This is my baseline. And I can go to step 11. Step 11 over here says, well, here's UGA, MGHA. That's the left side. Here's my right side. 1/2 mVB squared. Okay, low hanging fruit, you can see. M's cancel. So I do have an expression for VB, number 12. VB equals square root of 2GHA. Okay, let's put that in your memory location A. Let's all do that. So now we have a launch velocity. The launch velocity is 2 times 9.8 times 22 square root store alpha A. Okay. So good news. Back to number 5. Number 13. Here's number 5 is now. Step number 5 is now. This is what we have. We have GHA equals 1/2 VC squared. All right, so here's equals 1/2 times VC. I'm kind of putting too much into one step. I'm going to back up a bit. I'm going to put a few more intermediate steps because I'm trying to cram too much into one line. So that's all right. That's VB. I don't want VB. I want VBX. So once again, VC equals VB cos theta. So let's put that. I'm going to put that in calculator memory location B. VC is VB cos theta because there's no x acceleration. So multiply that by cosine of theta. My theta is 23. Got it. Store alpha B. All right. And now, I guess that's good. Number 14. Isolate. Let's isolate H subscript C in step number 5. So if I look at number 5, here's H subscript C all by itself. H subscript C all by itself is going to equal GHA minus 1/2 VC squared, which is sitting there in my calculator memory. All of this over G. Unless I made a mistake somewhere. But I guess we're good to go. Let's see. I know H subscript A, that's the height at state A, which for me is 22. I just figured out V sub C. All right, let's see what happens. All right. 9.8 times 22 minus 0.5. $3.35 and some change. So this is our first energy analysis endeavor. H subscript C equals 3.358 meters. That's the answer to part A. So before we move on, though, again, learn everything you can, you guys. There are 16 steps. So here's what's for sure going to happen. I know, we all know you're going to get the right answer. That's not new. That is not a mystery. The fact that you're going to look and listen. You're going to look at what I'm doing and listen to what I'm saying, and you're going to get the right answer because you're basically just going to use your numbers, not mine. But here's the big difference: is learn from steps 1 through 16. So I'm just trying to keep nudging you into doing that so you get better scores on the exam and you learn deeper. It's about exams, but it's about when you get your first job as an engineer or a technologist, how do you learn stuff? How do you master stuff that you don't know? And it's all sort of aimed at that scenario. All right, done with part A. Part B says, here's part B. What happens? What is H subscript C if skier adds a 10 kilogram backpack? So you do the same jump again, but now you're wearing a 10 kilogram backpack, and the answer is nothing new. Nothing new. H sub C remains unchanged. Remains 3.358 meters. And that's because, look at my equations. Number 19. Mass doesn't play a role. Mass has no effect because mass got canceled. Mass was canceled way back here in step 3. So mass disappeared in step 3. It disappeared again in step 11. And I mean, ultimately, look at this is the expression we used. We found ourselves to this expression, step 15. And nowhere in step 15 do you see any allowances for mass. This is all mass independent. This particular problem might not always be like that, but it is here. So that's why the answer to B is the same as the answer to A. Okay, that's our first. This is our first energy analysis problem, and it is really it's there's this is the recipe, not too crazy. And when you practice enough, you guys, this will be common sense. You won't have to worry about you won't have to worry about wondering what the heck this is saying. This will become common sense to you. It's just keeping track of stuff. All right, keep working on that if you need to. I'm going to get chapter 8 quiz 2 prepared. Energy analysis, the ultimate analysis, the ultimate tool, the ultimate power tool. Chapter 8, quiz 2. So there's a few basic categories. By now, hopefully you're sensing the scenario. Okay, for every chapter, there's a few basic categories. And I'm just mentioning that so you don't worry, you don't wonder, like, are there an unlimited number of categories that I have to deal with? No, there's not. There's a couple of basic operations for every chapter, a couple of basic categories, and you have to get familiar with those and not worry about, again, a never-ending series of weird situations. Just a certain number of weird situations. All right, so this is a graph. So we're gonna do graphical analysis for sure. All right, so let's begin. This is we have a potential. So it turns out these are a big deal. These potential energy graphs, I'll just write that. These are used a lot. Potential energy graphs. Turns out they're pretty popular, pretty widely used because they allow scientists and engineers to study energy, energy transformations, potential energy graphs. So this is deserving of its own special category within chapter 8. All right, so now what we're looking at, I think of this as a bead on a wire. Imagine that you have a wire, just a straight wire. And then sitting on that wire, you have a little glass bead like this. Here's a glass bead. All right, so you have this glass bead, and this glass bead is constrained to move in one direction. So let me do that again. Glass bead sitting on a wire there. Okay, so this is for sure one-dimensional motion. And the only reason I'm mentioning that this is one-dimensional motion is because when you look at that graph, you might think this graph is showing two-dimensional motions because it actually looks like a hill. Like here, like if I start here, I'm starting out here. I'm starting out at the trough of the hill or the valley, and then I'm walking up the sides of the hill. And then as I'm walking up the sides of the hill, I get to the plateau, the flat part, the plateau. And then if I go over here, well, if I'm walking up this side of the hill, this grade is even steeper, and this plateau is even higher. So even though it looks kind of like I'm going mountain climbing, I'm not. Although the terms I just used are very often used when we talk about potential energy graphs, even if it's one-dimensional motion. So you'll hear terms like valley, grade, plateau. What else did I use? Maybe even slope. It's a pretty steep slope, grade, slope. And I guess whatever. So these these mountain description terms are used in these diagrams a lot, even though, again, even though it's one-dimensional motion. So what's going on here is I have a particle. This particle is sitting right here. It says, according to my numbers, it says the particle is sitting here precisely at 4.5 meters. The particle is released at x equals 4.5 meters, which is maybe right about there. So this purple particle, maybe I'll use red since I'm using a red bead. This red particle, because I did use that analogy as a glass red glass bead. So there. All right. There's my particle sitting at 4.5 centimeters. That's my starting point. And if I'm reading this, it has an initial velocity going to the left, right? Like this. So kind of hard to read. Maybe I'll make that a little bit thicker. I start off going leftward. Okay. And now the question is, can this red particle make it up the hill and make it all the way to the top of that plateau? And again, I'm using a two-dimensional mountain term. I'm using mountain climbing terms, but it's just a bead on a wire. So then ask yourself, before we get into it any further, what could explain these changing potential energy curves? You know, why when this bead moves to the left? So the bead is currently moving to the left. How do you subject it to different potential energy? One way, maybe think about it like this. Maybe think of a magnet. Maybe this red bead, maybe this is a little magnet. So maybe this is a little tiny magnetized bead. So I'm just going to stick with that. I'll just say, for the sake of conversation, this is a magnetized, it doesn't have to be, I'm just making it up. This is a magnetized red bead. And one way you can kind of mess with it as it's moving around is to have magnets. So if this is a magnetized bead and it's starting off going to the left, maybe it's encountering some magnetic fields. And that's actually a common thing to do in practice in a number of situations. All right. So the question is, does this red bead have enough oomph to make it to the top of this plateau, or is it going to run out of energy? If it runs out of energy, it might stop here, for example. And that's what we have to figure out. We're going to have to figure out if my bead makes it to the top of the plateau, and if it does, what is its velocity? Or if it doesn't, where exactly does it run out of gas? All right, so I'm going to, you know what I'm going to do? I'm going to just erase this. So I'm going to have a going in position. Number one says, I'm going to assume, or I'm going to even better guess. I'll guess bead, which is the object. Bead makes it to energy state C, or no, energy state B. Okay. So here is the red bead at the very start of the slope, right there. Here's the red bead at the very tip top of the slope, right there. Okay, so let's do energy analysis. This is energy state A. This is energy state B, and I lost my magnetic bead right here. Okay, this is energy state B right here. So I've identified my two energy states, A and B. I don't know if it makes it to B. It's just a guess right now. I have to, so let's see, ID energy states. ID energy states is now officially done. Step 2 is let's worry about a baseline, establish the baseline. I'm going to do my baseline right now. And they kind of have done it for me. I could override it. I could kind of just ignore what they're doing, but there's no need to in this case. Here's my baseline, right? 1 second. Uh-oh. Baseline. It's gone. All right, so let me redraw my baseline. That's my baseline. And make it clear what you're doing. This is my baseline. The baseline is where you have no potential energy. So potential energy equals 0. Okay. ID my energy states, establish the baseline. And you know what I should do too? Show vectors. I really should include that because, all right, so here's my bead is going to travel from energy state A to energy state B. That's good. So that's my displacement. All right. So, and then let's apply the EAM equation. A, B, C, D. Apply EAM equation. And this is going to get pretty easy. It might not be really straightforward now, but we're not that far because it's going to start to sound familiar. I have some energy at A plus some external forces adding or stealing energy means I'm going to end up with that total amount at B. So business as usual. I guess I'll go here. Number 1. Pardon my numbering scheme, but at energy state A, I could have some kinetic energy. I could have some potential energy. And then on top of that, in addition to all of that kinetic energy and potential energy, there could be an outside force adding or stealing energy. And that's what this term is for. And then as I go from A to B, the work non-conservative work happens here, happens during the journey from A to B. Like again, a gust of wind, or maybe it's a magnetic force. Well, that's a gust of wind or a tow rope or friction or a little jetpack. Maybe the bead is wearing a super teeny tiny nano jetpack. Those are examples of non-conservative work. So at B, I might have some kinetic energy and I could have some potential energy. And notice I'm writing potential energy, not gravitational potential energy. So there's no mention. This is not a gravitational potential energy. In this case, it's just potential energy. It could be gravitational or elastic or magnetic or electrical or chemical, whatever it is, we don't know. So we're not caring about the kind of potential energy it is in this situation. All right, so you know what I'm going to do? Well, low-hanging fruit. Low-hanging fruit. Do I know any? Well, I know this is equal to 0. There's no mention. There's no mention of any external force donating energy or stealing energy. No mention of any non-conservative forces doing non-conservative work. So that goes to 0. And then, so I guess that's it for my low-hanging fruit. So number 3, you know what I'm going to do? Solve for K sub B. Solve for the kinetic energy at B. I know one thing. If K sub B is greater than or equal to 0, the bead makes my little red bead, reached reached point B. So maybe my little red bead just makes it to point B and completely runs out of gas, but it made it to the top. Maybe it makes it to point B and has some leftover energy and keeps going, or maybe it falls short. If it falls short, my kinetic energy should be less than zero, because I can't have negative kinetic energy. Remember what kinetic energy is. Kinetic energy is 1/2 mv squared. These all are always positive. 1/2 is always positive. Mass is always positive. Anything squared is always positive. So you know one thing, kinetic energy is always greater than zero. Changes in kinetic energy could be less than zero, but kinetic energy is always zero. All right, let's keep going with energy analysis. Number 4. All right, so here's my new number 1. My new number 1 says the following. My kinetic energy, 1/2 mva squared, my kinetic energy at A, that's my kinetic energy at A, so I'm taking care of that. And then here's my potential energy at A plus my potential energy at A, UA, got it? There's no non-conservative work. It equals the kinetic energy at B, which I need to solve for that, plus the potential energy at B, which is also given. For me, it's 35. I'll just write it as UB. Okay, so 5. All right, so here's case of B. The kinetic energy at B is simply going to be the kinetic energy at A, 1/2 mva squared, plus U subscript A, got it, minus U subscript B. Let's do this with numbers. Kinetic energy at point B is 1/2 times mass. My mass is 0.897, 0.897. That was given to you. Kilograms times velocity at A was that, yeah, that's given. 7.84. 7.84 meters per second squared. All right. That's 1/2 mva squared plus U subscript A. U subscript A is 15 joules minus U subscript B, which is 35 joules, according to my numbers. Okay, so let's put that in the calculator. What is 0.5 times 0.897 times 7.84 squared plus 15 minus 35, 7.56. So you know what? My red bead made it, 7.567 meters per second. I'm going to redo that, store alpha A. So 0.5 times 0.897 times that velocity at energy state A, which was given, 7.84 squared plus potential energy at A given as 15 minus the potential energy at B, which is also given 35. All right, minus alpha A. So that's it. I've made it. The red bead has made it to the top of the mountain, reached the plateau, because I have some kinetic energy. I still have some kinetic energy. So in this case, solve for VB. Okay, so, well, I know kinetic energy. Kinetic energy is simply 1/2 m, and I'm using subscripts here, VB. If kinetic energy is 1/2 mVB squared, then I can simply say VB equals 2 times that kinetic energy at state B divided by M. and all of that square root. And I know everything here. I just figured out, oh, and KB, here's a little mistake. Let me fix this mistake. Units, this should be joules. So shameful. Okay, let's see what the velocity is. 2 times alpha A divided by 0.897 square root of all that, 4.107. 4.107 meters per second. That is my velocity at B. This is the answer to part A. So there's our first, and really there's not a whole lot more. There's nothing, I don't think there's really anything brand new. You've seen now potential energy diagrams, and then there's just a bunch of ramp problems and other things that are all kind of in the same category. Okay, this is the answer to part A. All right, that's just part A. Part B, what's that's the magnitude. What's the direction? Okay. So in your green sheets, much video time was spent talking about potential energy graphs and the relationship between potential energy, work, and forces right here. So not to go through it from start to end, I'm just saying, look how much fun this is. I'm just saying right here, force, work, and potential energy. Those are all entwined. They're all related. Force, work, and potential energy. I'm basically going to come in at the very end of the story, but you really do need to digest the whole story because it makes a difference. It's just the path you've chosen. You've chosen a path where you actually do have to have insight all along the way, but I'm going to start here. And I'll call this step 9. So I'm getting started on part B. What's the direction of this force? What is the direction of this force? I will call this step 9, 8, 9. Okay, so aha, this is an aha moment. Aha. Force equals negative slope of a potential energy, U, a potential energy versus position graph. Versus position graph. So major foundational step, the relationship, look at all the stuff it's tying together. It's tying together work and potential energy and force. That's obviously important. All right, so there's a lot that needs to go into the understanding of that, and you really do need to get that understanding by watching the videos. But here, okay, what is slope? Okay, what is slope? What is the slope? And I remember slope. Slope M. Remember, M stands for slope. M equals rise over run. And generically, we used to say delta Y over delta X. And here we're saying, well, specifically here in our case, it's delta U over delta X. So that's the slope. Let's find out the slope. So here's the slope. Delta U is final minus initial. So again, I am focused on this left side path. This is the bead, the little red glass bead going to the left. So that's what I'm focused on. Delta U is final minus initial. So let's do final minus initial. Final would be UB. The bead ends up at potential energy B. It started out at A. all over this x value, because this is the x value at UB, all over 2 minus this x value minus 4 meters. So with numbers, here's my slope. Slope is UB, which is 35, minus UA, which is 15, right? UA is 15, UB is 35 joules, all over -2 meters. So you know what that equals? That slope is 35 minus 15 divided by -2 is -10. -10 joules per meter. But as mentioned, I guess I'll go to a step 11. Here's step 11. Remember, force is negative slope of a negative slope of a potential energy versus position graph. Okay. So now number 12. The force equals positive 10 joules per meter. What is a joule? So a joule is the same as a Newton times meter. That's a joule all over meters, which is why the final answer is the force exerted on the red bead as it moves leftward is equal to plus 10 newtons in the I hat direction. Okay, that's part B. So we know what's going on with the bead. As the bead is moving to the left, we actually can say a lot. As the bead makes it, or as the bead is going to the left, I know one thing. I know the bead can make it to this point right here from okay. This bead can make it to that point. So this would be energy state A. This is energy state A. This is energy state B. So my bead can make it to point B, just like this bead can go up this ramp, right? But as it's moving to the left, it's encountering a rightward force, so like a gust of wind. So this is the force acting on it as it moves to the left. That's A and B. What about C? C says, all right, well, that's A, B, A, B, C. C is the direction. So this is the direction. So plus, that plus means plus X direction to the right, as mentioned. The bead encounters a rightward force. So that is the answer to part C. All right, so there's, the value is 10, the direction is plus X direction, plus X or plus I direction. So now we say we're going to have the same situation, except now the bead is moving to the right. So let me erase some stuff here. By the way, I need to provide a clarification. Is this energy state here, are these two energy states, this energy state A? So here's a question. Are these equivalent? Is this energy state A right here the same as this energy state A? And the answer is yes, those are equivalent, because during the path from the first A to the second A, there's no change in kinetic energy. So as I'm going from the right side A to the left side A, there's no change in kinetic energy, and there's no change in potential energy. So I should say does equal to 0. There's no change in kinetic energy and there's no change in potential energy. So whatever's true at A on the left side is true of A on the right side. So now we turn our direction. Let's go ahead and play this, take the identical approach, except now the bead is going to the right. And I have a feeling that we're going to run out of gas. At least I hope so, because that's going to be a different situation. So the bead is moving to the right. Let's make sure that's clear. My bead is moving to the right. There it goes. And when it moves to the right, it's going to start up the hill right here. Okay. And the same conversation, can I make it all the way to the tip top? Can I go all the way up that hill and reach the plateau? So let's just do energy analysis again. This is state A. This is state B. And just for the sake of completeness, this state A right here, the yellow highlighted state A is identical to the blue or to the green highlighted state A, because there's no change in kinetic energy and there's no change in potential energy. All right, now let's just do the same thing. Let's do everything set up for us. Let's just do energy analysis. Okay, so this is part D. Is it? Yeah, part D. The energy at A plus whatever forces add energy or steal energy equals the energy at B. Nothing new there. I'm going to peel apart this onion, the kinetic energy at A. So I do have some kinetic energy at A, just like last time. I do have some potential energy at A. I don't have any non-conservative work because there's no mention of it, but I'm dragging it along and then crossing it out right about now. But at B, do I have kinetic energy at B, and I have potential energy at B? So let's low-hanging fruit. This is going to equal 0. Okay, no mention of, there's no description of forces adding or stealing energy. So number 3, here we go. I'm going to isolate KB again. KB equals KA plus UA minus UB. KB equals KA plus UA minus UB. And here's the same thought process. If K sub B is less than 0, that means the following. Bead, this little red bead does not make it. Bead doesn't reach point B. Okay, so it's that same rationale. Number 5, kinetic energy at B in this situation when the bead's going to the right is going to equal Ka, same thing, 1/2 massive A minus 0.867897. Fine, times my velocity. I'm just kind of remembering this. My velocity at A is 7.84 meters per second squared. So there's kinetic energy, 1/2 mv squared. So I'm done with solving for KB. There's Ka. Now I'm going to add UA and minus UB. I do have to go through and make a typo. There's a typo here. Let me fix this typo right now. All right. This should be C.
C. Yeah.
C. This should be energy state C, which corresponds to U sub C, which means I'm just going to go through and quickly do a little update. This should be C. This should be C. And this should be C. And then this should be C. If K sub C is less than 0. And then last but not least, this should be C. And then I think I'm good to go. And I'm just calling it C because I'm ending up at what the problem depicts as potential energy at point C. So just to keep consistent with that. If K sub C, all right, that's good. So number 5, again, this should be KC. All right, so K sub C equals K sub B. This is K sub B, 1/2 mv squared minus, except darn it, one more escaped. Where did that? Okay, here. Jeez. Messy. All right. KAUA, WNC, KCUC, KC equals KA plus UA minus UC. Number 3 is good. If KC is less than 0, B doesn't reach C. Number 4 is good. K sub C equals KA plus UA. UA for me is 15 joules minus UC. UC for me is 45 joules. All right, so now calculator says K sub C equals 0.5 times 0.897 times 7.84 squared plus 15 minus 45. I get a negative number, so I don't make it. K equals negative 2 point whatever, 2.432 joules. Aha. B does not make it. B does not reach C. Does not reach point C. So now I have to find out where it stops. So that's a big step. I mean, you're thinking that's a lot of work just to figure out a stop. But you got to go through it. That's the analytics. So I'm gonna do a little redraw here to make things really easy to read because things are getting a little bit cluttered. Okay, so here I'm just going to draw this segment of the graph and stretch things out a little bit. Again, my goal is just to make things easier to read. So here is C all the way to A. Okay. So let me just, now that that's way easier to view like this, I'm going to call this is the bead right here. This is the bead when it was just starting up the ramp. This is the bead at the top of the ramp, which it never quite reaches that point. It doesn't reach the top of the ramp. The bead basically stalls out somewhere here, and I don't know where that is, but that's what I have to find out. So I have energy state A right here. This is the bead right as it's climbing up this slope. Here's energy state C right here. I don't make it to C. I have shown that this B does not have enough energy to reach C. So it stalls out here. I'm going to call this X. Just make up X. This is energy state X. Okay. And I have to find out this location. So here, if I was going to go back here, this is energy state X right here. This is where my bead stops somewhere. And I have to find out this coordinate right here. I'm going to drop this line right here. The question is, where exactly does this bead stop? And right here, this is the dollar sign. That's what I got to find right now. All right. So, and I just redrew it just to make it a little bit easier to look at. Number 14, I'm going to go way over here and maybe change the color for step 14. Step 14. Here goes. Energy at A plus non-conservative work equals energy at X. Got it? Number 15, energy at state A. Yes, I could have some kinetic energy. I could have some potential energy. I don't have any external forces adding or removing energy, but I'm going to drag it along for a ride just for another step. And then at X, I could have some kinetic energy and some potential energy. And then let's talk about low-hanging fruit. Let's just deal with the obvious right now. And there are some obvious simplifications we can make. For example, this is equal to 0. Kx equals 0 because my bead stalled. Bead runs out of gas. The bead stalls. The bead stalls at some point. It didn't have enough oomph to get up to the plateau, the flat top of this mountain. This is equal to 0. There's no mention of any external forces adding or stealing energy. And I guess that's it. All right, so for my low-hanging fruit. Number 17, right here. I'm gonna solve for U sub x. Find U sub x. Find the potential energy at the point at which that bead runs out of gas. Ready? U sub x is equal to Ka plus UA. And I guess that's it. Look how easy this is. So I'm just going to go write it right in here now. Ka is 1/2 mVA squared. Subscripts are really important. Plus UA, and UA is 15 joules. Okay. And this is it. This is the potential energy that my red bead has attained. It has attained 0.5 times 0.897 times 7.84 squared plus 15. Is that right? UA plus 15 or 42 and some change. I have this much potential energy, 42.567 joules. All right, so that's great. I know U sub x. So now I can figure out where this particle ran out of gas. Let me just draw some grid lines here. Okay, so here's a vertical line going through energy state A. There's a vertical line going through energy state X. Good enough. There. And then here's a vertical line going through energy state C. I'm just taking the time and trouble to recreate my own graph, but I'm doing this because it's easier to read. Otherwise, things just get too cluttered. Here's this horizontal line, and then this horizontal line. And then let me position this. So here's my quickly recreated graph. Wasn't too much trouble, especially it's to me a lot easier to read this now. Okay, I know this value because I'm all about position. I know the position at A. At A, I'm right here. This is 5 meters. So this position right here is 5 meters. At C, my position is 6 meters. This is 6 meters. So let me get a thicker pen. Okay, once again, Here's the 5 meter mark right here. 5 meters. 6 meters is right here. 6 meters. And this is my dollar sign. That's my dollar sign. Where do I run out of gas? And this is a bead on a wire. There's no real physical hill. It's just a bead on a wire. So I'm just going to do similar triangles. Okay. And this is what I'm talking about. Similar triangles is just like a middle school thing, I guess, or whatever, 9th grade. But I have a triangle. I have this purple triangle that looks like that. And then I have this big orange triangle that looks like this. Do that. You can do this whatever way. This is just a way. This isn't the way. It's just a way of doing it. We all have our preferences. We all have our idiosyncrasies. This is just mine. You can do it your own way. But I have this purple triangle and this orange triangle. And I know enough about this to find that dollar sign. All right, so as far as the purple triangle is concerned, look at this dimension of the purple triangle. Okay, I'm going to call this X. X is that dimension. Here's the vertical leg of this purple triangle. The vertical leg of this purple triangle is U sub X minus U sub A. Got it. Play the same game with the orange triangle. Here's the horizontal leg of the orange triangle. This is 1 meter. Because from 5 meters to 6 meters, that's 1 meter. Here's the vertical part of this orange triangle. It's UC minus UA. Okay. UC minus UA. So now it's off to similar triangles. Number 18. Okay. So similar triangles means the following. It means that X, I'm looking at the purple triangle. So if I look at the purple triangle, X over UX minus UA is going to be the same as the orange triangle. So what corresponds to X? 1 meter. So the purple triangle's horizontal leg corresponds to the orange triangle's horizontal leg, just like the purple triangle's vertical leg, which is UX minus UA, corresponds to the orange triangle's vertical leg, which is UC minus UA. So now I'm just going to solve for X. X equals UX minus UA all over UC minus UA. And let's get a number on that. (42) minus UA is 15 divided by UC, which is 45 minus 15, 0.918 and some change. 0.9189 on and some change meters. And then my answer is going to be number 19. Number 19. Aha. Final position. Final location when it stalls. The stall location is this. 5 plus 0.9189 meters. 5 meters. Because this is 5 meters right here. And then I got to add that chunk of change. So my answer is 5.918 0.91 meters. That's the answer to part C. Done. How's the time doing here? 2:30. Let's just finish this and have a nice long break since this is like drinking from a fire hose. All right, step 20. This is the answer to part C or part D, I think. Direction. Yeah, this is the answer to part D. And I'm just going to quickly fast track the conversation I had previously to say, well, what's the force? Since the force is the negative slope of this graph, I'm going to say force equals negative slope, negative change in U over change in X equals negative U final, which I can just say is U final is UC minus U initial is UA all over the corresponding position. My X final is 6 meters. My X initial is 5 meters. U sub C is given to me as 45 joules minus 15 joules all over, and I can't forget this negative sign, all over -1 meters. So if I keep track of these negative signs carefully, I have 30 negative, positive 30. I have positive 30 newtons. So that's the answer to E. E just wants the magnitude. Force is 30. F wants the direction plus X direction. So when the bead is moving to the right, it's feeling a gust of wind pushing it. When the bead is moving to the right, hang on. I guess this is right. Is this right? Let me just sanity check myself. That's 30, negative 30, positive 30. Okay, that's right.
It's not -1, it's +1.
Yeah, you're right. Thanks. Thank you, Ty. Thank you. That is correct. Very helpful. So it's not negative, it's not positive 30 newtons. It's negative 30 newtons. But the magnitude is indeed 30. And now the direction, that's what I need to change because again, 6 minus 5 is equal to 1, not -1. And it's the negative X direction. So when the bead moves to the right, it's feeling a gust of wind, for example, pushing it in the negative X direction. And that's the answer to part F. What a problem. We have survived. It's now 2:34. I will see you at 2:44. See you at 2:44 p.m. because we all need a break. Am I really that late? So maybe I am. Anyway, maybe I was distracted with my time calculation, but maybe not. Let's do next one. Chapter 8, quiz 3. So you just lived through a potential energy graph and a bunch of stuff that's associated with it. That's, again, sort of a subspecialty. Chapter 8, quiz 3. Okay. Next up, chapter 8, quiz 3. Looks like this. Energy analysis, still energy analysis. Okay, here goes. This is a spring mass system. This mass, this orange block is attached to us.
Back from a search.
My phone thought Google thought I was talking to it. I'm not talking to you. All right, so this orange mass is attached, this orange block is attached to a spring, hence the term spring mass system. And then this is what's happening. This orange block, think of a pinball. Think of a pinball, the old school pinball arcade machines where you pull back on the handle and you let it go and it launches. So basically this spring launches this orange block from rest and it encounters a friction patch. And the question says, the part A says, how much heat got generated? So let's start with part A. And I know one thing, all of this friction that gets created, what does friction create? It creates heat. So part A is saying, it's basically saying, well, it is saying how much heat does friction create? How much heat is created by friction? How much heat is created by friction? So we have to get smart about friction here. Here's my first thinking. I'll find the work. I'll find the work done by friction. Because when friction does work, it creates heat. I'll find the work created by friction. And I know I'm an expert at this point. We're all experts on how to calculate work. The work created by kinetic friction. It's not static friction, it's kinetic friction because things are moving. There's scraping going on. It's not held in place. But the work created by friction is just same old. It's going to be this. In general, by now you should be really familiar with work is F dot dr. That's the dot product representation. This is the magnitude angle representation. So just a brief 20-second recap on the definition of work, and theta is the angle between my displacement vector and my force vector. So here specifically, the work done by kinetic friction is that integral of the force, and the force is not just any generic force, it's the kinetic friction force. And I'll go right to magnitude angle. Again, I just refer to this as magnitude angle format, and I refer to this as dot product format. And they mean one and the same, and you should definitely review your notes and past lectures. You should be watching these recorded Zoom sessions anyway. I'm kind of assuming you do. It would be eyebrow raising if you don't, but rewatch them if you need to relive that explanation. FK, and you know what I'm going to do? I'm going to do dx cosine theta. So I'm just taking my generic expression for work and I'm sort of personalizing it for this particular situation. Theta is the angle between my dx vector and my f sub k vector. And let's talk about what those vectors look like. Here's my ground. So I'm just going to draw. Here's the ground right here. And then here's my orange block sitting on the ground. So I'm just doing a little redraw here. And what are the forces acting on this orange block? Well, as it moves along this friction patch, so we're seeing that right here, it's sliding along this frictiony area, a rough patch. I'm thinking maybe this block was sliding along ice, and then it transitions from ice to cement, a cement surface, for example, or a wood surface, whatever. All right, so as it's going along this friction patch, there's a friction force acting on it. And this friction always opposes velocity. So if it's moving to the right, friction is oriented to the left. So this is F sub K oriented to the left because the displacement is, as mentioned, to the right. You launch it. It comes screeching out of this launcher going to the right. So this is my displacement vector. This is my force vector. You can see the angle between those two vectors is theta equals 180 degrees. Theta equals 180 degrees. So that answers theta. So let's keep going with number 3. What comes after 3? Number 4. Number 4 says the work done by friction is equal to mu sub K mg dx cosine theta from 0 to big D. So let's talk about all of this for a second, because that kind of came out rather abruptly. All right, mg. This is my normal force. What do you get when you multiply? What is mu sub K times mg? This is kinetic friction. Okay, so maybe we probably should do a very brief little Y force inventory, just so we don't take too many shortcuts. This is the weight force acting down. So mg is oriented downward. This is my normal force going up. And you can see that if I'm sitting on a flat surface, that normal force has to be the same as the weight force. But let's just do a Y force inventory just to be airtight, which says the sum of all Y forces equals F sub n going up minus mg going down. And Newton's second law says that, well, that's mass times acceleration. And your next step is to always say something about acceleration. And I can say this, A equals 0, because there's no plus or minus Y motion. The block does not leave the floor. It's moving left and right, left or right, but it's not moving up or down. So this is why we're saying, you could see this maybe immediately. The normal force is the same as mg. All right, so that's why I'm saying the normal force is simply the weight force. And I know that F sub K, the kinetic friction force, we know this hopefully by now very clearly. All right. And then I guess I'm good to go. Oh, and remember, always, without even thinking about it, this is the smaller position, and this is the greater position. So you never have to worry about, well, should this be, you never have to worry about, well, should I call this D and this 0? You don't ever have to worry about that. Or you might say, should I call this 0 and minus D? You don't have to worry about that. Or maybe this is minus D and blah, blah, blah. It's always this. It's always the lower position. This is the lower position. This is the higher position. In terms of the sign, the algebraic sign, the positive and negative work, because work is either positive or negative. This is the term that will take care of that, this cos term right here. So let that figure out the algebraic sign of your work. Everything else is just straight procedure, straight, cookie cutter. All right, so here is the work done by friction. It equals mu sub K. I'm bringing everything out to the left side of the integrand. Mg, so these are all constant. Mu sub K is a constant. Mg is a constant. Cosine of theta is a constant. And I'm left with the integral from 0 to D of dx. So this becomes mu sub K, which I know, mg, which I know, cosine of 180, which is -1, times D, which I know. So when I put that into my calculator, I get 0.201 times 3.1 times 9.8 times cosine of 180 times D, which is 8.3, negative 50 and some change. This is the work done. This is the work done by friction. And to be honest, here's a helpful little sidebar conversation. Friction always does negative work. Friction is always trying to steal energy. Kinetic friction never adds energy. Joules. All right. So this much heat. So I'll say number 4, 5, 6, 7, 8. Aha. This much heat got created. Plus 50.682954 joules of heat got created by the friction force. Okay, so that's how much heat got created. And this is the answer to part A. All right. All that friction work does something. Why do you do work? You do work to produce something. And what gets produced here? Heat. Sometimes you want to produce heat. Sometimes you want to avoid producing heat. But that's how much heat got created. Part B says the maximum kinetic energy of the block. Okay, so I think I'm going to do another supplement. And on the exam, you guys certainly feel encouraged to crank out a lot of supplemental drawings. They help. All right, so here's my orange block. This is my orange block when the spring, when it's loaded. This is maximum spring compression. And then you launch it, you let go, you fire the mechanism, and the orange block goes skating across this frictionless surface, which I'll show is right there. And then it skids to a stop somewhere over here. Okay, so I'm going to call this energy state A, energy state B, energy state C. And again, this is my friction. This is when my block encounters friction. From there to, from there to here. All of this is frictiony. This is my sticky surface. This is my rough cement surface. All right, between A and B, this is my friction-free surface. So maybe think of this as just a sheet of friction-free ice from A to B. That's this friction-free ice, no friction whatsoever, no friction losses, just friction-free ice. Okay, so A, this is when this is happening at maximum spring compression. Max spring compression. This is the release point at B. This is the release. This is when the block is released from that spring, and this is where it skids to a stop. Skids to a stop. All right, so this is my redrawing, and these are very helpful to do and to read. All right, so what's my maximum kinetic energy? I'm going to do this. I'm going to do an EAM. So step 8, step 9. Step 9, I'm going to do an EAM from B to C. Okay, so my energy at B plus my non-conservative work, which is definitely not equal to 0, equals my energy at C. I gotta stick to the recipe, which means I have to worry about a baseline. The baseline is pretty simple. This is just my baseline. So nothing super fancy. This is my baseline. Everything's just happening horizontally. There's no change in gravitational potential energy. All right, so let's keep going. Step 10. with my energy analysis between B and C. Step 10 says, well, at B, which is the release point, I'm going to do it like this. I might have some kinetic energy at B. I might have some gravitational potential energy at B. I might have some spring. This is called elastic potential energy because now, in addition to gravity, I have spring. So gravity, there's gravitational potential energy and there's elastic potential energy. So whenever you see USA, for example, is stored spring potential energy at A. Stored spring potential energy at state A. Okay, so this is a second kind of potential energy. All right, plus WNC, which is not going to be equal to 0. That's the friction. And then at C, might have some kinetic energy, might have some gravitational potential energy, might have some elastic potential energy. Let's talk about the low-hanging fruit. Here's the low-hanging fruit. At C, I've skidded to a stop. There's no kinetic energy. There's no potential energy. There's no spring energy. So make sure you know why those are 0. There's no kinetic energy because it skids to a stop. There's no gravitational potential energy because I'm just sitting there at the baseline. And the baseline is where, again, UG equals 0. And there's no spring energy because the spring is relaxed. In this portion, spring is relaxed. Spring here, in this region, the spring is relaxed, meaning no stored energy. So look at what step 10 becomes. Step 10 becomes KB equals, oh wait, there's more low-hanging fruit because this is equal to 0 for the same reason, and this is equal to 0. So you know what we have. And make sure you guys, it's probably a good idea if I don't explain everything in full detail and let you kind of pick up the slack. But this is what I have. My kinetic energy at B, which is equal to maximum.
Any way you could scroll down a little bit?
Okay. As soon as my box encounters the friction patch, I'm going to slow down. So I'm going to call whatever kinetic energy I have at B, that's my maximum kinetic energy. That's what I'm looking for here, equals minus there. There you go. Okay. Equals, what's doing the non-conservative work? It's the work done by the friction force. And we already have an answer on that. So here's the answer, equals negative. The work done by friction is right here. It's sitting right there in step 7. And this was the work performed, the work cranked out by kinetic friction. So that's just sitting there, negative 50.682954. And that's our answer. That's why you can see the answer to part A and B are the same. But you kind of had to go through these steps to show, you had to show why they were equal. You could maybe describe it, but you can describe it, but you have to show it analytically. Part C. What's the initial compression of the spring? So check it out. When the box is at that far left side at state A, look at my spring. My spring is going to be completely very much energized. So here's my spring, again, compressed a lot, like that. So I want to know, here, this was the spring. This is the spring in its relaxed state, just sitting there, minding its own business. spring, relax. And then this is the spring when I really load things up, when I really cram this box. So this is relaxed. This is compressed. And the question is, how much did it get compressed? So I need to find out this distance from here to here. This is what I'm after right now. This is the amount of compression. All right, so energy analysis to the rescue. I'm going to do between A and B. Energy at A plus WNC equals energy at B. I have my baseline already established. I don't need to worry about that anymore. My kinetic energy at A plus my gravitational potential energy at A plus my spring potential energy at A plus WNC. And then B, at energy state B, I have to worry about kinetic energy, gravitational potential energy, and spring or elastic potential energy. Let's go after some low-hanging fruit. This is equal to 0. Because when you load up this orange box, when you basically smash it all the way towards the left to energy, to really compress that spring, it's sitting there at rest. It's not moving. UGA, there's no gravitational potential energy because of my baseline. However, USA is not equal to 0. This is equal to 0. And again, this term, and it pays to remind everyone what this term means. This is the non-conservative work occurring from A to B. Okay, and there is none because we're on ice. This is ice. There's no friction here. So that's why that's equal to 0. All right, and then at energy state B, I have pure kinetic energy, nothing else. So no gravitational potential energy because of my baseline. The spring is now completely relaxed. So step 14 says the following: USA, which is 1/2 K X subscript A squared equals KB. Remember where this came from. This was derived in your green sheets. In your green sheets, the elastic potential energy, also known as the spring potential energy, is shown to be 1/2 K X squared, where X is the amount of elongation or compression, amount of elongation or compression. In this case, we're dealing with a compressed spring, and K is the stiffness constant. Again, the spring that I have on my garage door is pretty stiff compared to a spring that you might find in a ballpoint pen. So springs come in all kinds of variety, but this is the elastic potential energy. Springs are like batteries. Springs store energy. So there's my energy just sitting there in my charged up spring. On the left side, on the right side, it's KB, and I already have an answer for KB. I know what that is. So I'm going to just isolate XA. XA is going to equal 2 times KB, which I have a number on that, divided by K, and I know what that is. That's the spring stiffness constant, square root. So let's see. KB. KB is sitting right here. This is KB right there. So I for sure have a number on that. That's my maximum kinetic energy. And K is given in the problem statement for me. K is the spring stiffness constant, or 630 newtons per meter. And I guess that's it. Okay. Let's go with that. 0.401 and some change. We're done. That's the amount of compression. If I squeeze my spring that much and then launch, I end up at this distance before I skid to a stop, as I skid to a stop. This is the answer to part C. Okay, so it is now time for our next quiz, 316. Okay. Number 4, quiz 4, chapter 8, quiz 4. Is next, chapter 8, quiz 4. Only 2 more quizzes. That seems oddly, it seems not enough. There should be more quizzes, but maybe not. Well, these are all pretty time consuming just because I'm making them time consuming. They're normal problems. They're very consistent with what you're going to see on exam 2, but I'm taking an opportunity to do a lot of reinforcement. It's now 3:17, 4:30 p.m. And now I think chapter 8, quiz 4. You should see it now if you refresh. Chapter 8, quiz 4. Okay. Let me know if you're seeing something different. Chapter 8, quiz 4. All right, this is a child sliding down a slide.
Hold up, Professor. I think you have the wrong problem for quiz 4.
Chapter 8, quiz 4. Let me double check.
Let me try it one more time, just to make sure.
Chapter 8, quiz 4.
No, my quiz 4 has like a box on a slope. not like
Chapter
that.
8, quiz 4.
Yeah, it's the same for me.
Okay, yeah, 67, 867. Huh, darn it, I wish that wouldn't do that. All right, let me make a little change. Chapter 8, quiz 4 should be 54. One minute while I swap problem 67 with 54. Chapter 8, quiz 4. Okay. All right. All right. As of right now, if you refresh, you should see this problem. Again, let me know if you can't. This should be chapter 8, quiz 4. Okay, so here is a child is sliding down a slide. So let's draw a slide. Here is a slide. There's a slide. This slide makes an angle of 36 degrees with respect to the horizontal. Here's the horizontal. This is 36 degrees. Okay. I'm going to represent the child with just a dot. So this is the child, this red dot is sliding down this slide right here. Okay. A child who weighs 262, and remember, weight equals mass times gravity. And here, mass times gravity is 262 newtons, which means M, if I need to deal with just M, the mass of this child is 262 newtons divided by G. So that's a little sidebar. Sliding down the 6-meter playground slide, that makes an angle. Let's draw the displacement vector. My child starts here. The child, it's not necessarily my child. This child starts here and ends up there. Okay. This is the displacement. Okay. I'm going to call this, I guess I'll just call this, I think I'm going to call this X because I think I'm going to end up rotating my coordinate system. That's my displacement vector. Maybe I'll just stick with blue. That's my displacement vector X. I'm going to call this energy state A. This is energy state B. Okay. How much energy? So it's another question of how much energy do I lose to heat? So my displacement is from state A to state B as shown by this blue vector X. But while it's moving in that direction, friction is going in this direction. Here's friction. Okay, this is friction. Friction is going up the slide as the child is going down the slide. And you can see this is the angle. This is the angle between those two vectors. I'm going to call this basically, what should I call this? I don't want to use theta. Well, I guess I can. Theta equals 180 degrees. Okay. So part A is how much heat gets generated. So this is very much a repeat of what we've already done. I need to figure out how much work friction does. Okay, so here, the work done by kinetic friction equals the integral of the kinetic friction force times the displacement dx. I have to make that a variable of integration times the cosine of the angle between them from 0. And this is a 6-meter slide from 6 meters. So a few comments here. As I said, I'm going from, so instead of X, I'm going from this X variable becomes dx. So this becomes my variable of integration. Cos theta is, I got that. So cosine of theta equals cosine of 180 equals -1. And that -1 is once again just saying what we already knew. We know friction, we know the friction force does negative work, and that's where the negative comes in. And just to repeat, this is always the lower position, the minimum position, the maximum position. Minimum, maximum. Let the cosine theta deal with the positive or negative sign. And I can go from step 1 to step 2. The work done by kinetic friction is equal to mu sub k mg. Hang on. I'm going to do mu sub k f sub n. It's not quite so simple. It's not sitting there in the flat ground. Dx cosine of 180 degrees from 0 to 6. Okay. Number 3. The work done by kinetic friction, keep going, min max, mu sub k m, I don't know what the normal force is. So you know what, this is a job for a free body diagram. Here are my forces. All right, I have the normal force. That's my normal force. This is my normal force, F subscript N. This is my weight force. It's going straight down. So we're back in the realm of force analysis method. This is mg going straight down. There's friction. I already accounted for friction. So here are the 3 forces acting on this child. Normal force going perpendicular upward from the slide surface, weight going vertically down, friction force going up the slide. I'm going to, now here's a question. As far as messing with your coordinate system, here's the question. Do I know acceleration direction? And I think I do. Do I know the acceleration direction? Because if I do, that's going to be your guidance for setting up your coordinate systems. And I think I do. I know this child is accelerating either, I think this child is accelerating down the ramp or up the ramp. I'm not sure if that's this child is accelerating up or down the ramp, but I do know one thing for sure. I know for sure the child is accelerating parallel to the ramp surface. So I'm just going to call this plus x. You have to worry about this. Plus x. That's my thought process. That's why I'm choosing that as plus x. This will be plus y. That's good, like that. Plus y. All right, and what if I'm wrong? What if the child is accelerating up the ramp? It doesn't matter. I'm just tapping into the fact that I know that the acceleration is either down the ramp or up the ramp. So I'm good to go with this. I'm going to decompose my weight force. So this would be the x component of the weight force. Would it be? Yeah. Okay. This would be the y component. I'm going to do a little adjusting. So it's good. It's good to do good old force analysis again, which is why in many ways, chapter 8 is the ultimate chapter. This is my decomposed vector. This is mgy. This right here is mgx. And then I have to play my angle game. I'm going to play my angle game. Okay. Well, here's how I'll just add some supporting grid lines here. I'm going to play my angle game. Here it goes. If this is 36 degrees right here, if this is 36 degrees, and if this is 90 degrees, and this is 90 degrees right here, because that's vertical and horizontal form a 90-degree angle. If that's 36 and that's 90, this must be 54 right here. This angle must be 54, this green angle. If that angle is 54, this angle must be 36. So I'll just go with that. So this ramp angle right here, this 36-degree ramp angle is according to my just sort of ad hoc, informal, game. If that's my 36-degree angle there, then it corresponds to this angle here, just again, based on what you heard me describe. All right. So having said that, if I do a very quick little Y force inventory, sum of all the y forces equals Fn minus mgy equals a, and then you always say something about acceleration, and acceleration is equal to 0 because the block stays on the surface. The only way acceleration is equal to 0 now is because I rotated the coordinate system. If I didn't rotate the coordinate system, then you couldn't say the acceleration is 0. But here I can. No plus or minus y motion. So that's an advantage in rotating your coordinate system. And which is why we're saying, this is why we can say the normal force is equal to mgy, which is mg cosine of that 36-degree angle. Maybe we should have left it as, well, I already used theta here, so that's why I wanted to avoid confusion. All right, so back to step 3. Here's my normal force, mg cosine of 36 degrees dx cosine of 180. That's it. And let me sanity check this because that's quite the string. I am saying this is f sub n. And I'm saying mu sub k times f sub n is f subscript k. And here's dx. So this is the displacement through which that force acts, and this is the angle between those two forces, which equals -1. All right, so let's get an answer. Let's get an answer for the work done by friction, which we know is going to be negative, but that's actually the amount of heat produced. So mu sub k is 0.15 times 262 times cosine of 36 times 6. Okay, this is equal to -190 and some change. Negative 190.7662073. Joules. Number 4. So friction produces that much heat. Work does that's negative work, but friction produces 190.7662073 joules of heat. That's part A. A RAM problem. These RAM problems again are popular. They're common because they require. You can see they require kind of a lot of analysis. But we're not done because part B says, what if this child starts with some initial kinetic energy? So it's as if the child is up here on the slide and starts running. You ever used to do this? You start running and then you basically just dive onto the slide. I'm not sure that's what this child did, but the child has an initial kinetic energy. So step 5, and then our task is for part B to find out what's the speed at the bottom. So EAM time. Okay, whatever energy I have at A plus the non-conservative work, which is not going to be equal to 0, is my energy at B. So my dollar sign's living in here somewhere, speed at the bottom. All right, number 6. At A, I could have some kinetic energy. I could have some gravitational potential energy. I'm not going to include springs because there's just no springs here, so I'm not going to clutter the desktop. There's no springs, but I do have some non-conservative work happening between A and B. And at B, I could have some kinetic energy and I could have some gravitational potential energy. And I have to say, this is my baseline. Can't forget that. That is a mandatory requirement. This is my baseline right here. Wait for it. One minute while I regain control. Okay. Baseline. All right. So let's go after some low hanging fruit before we move on. All right. UGB, this was UGB. This equals 0 because that is at my baseline. Baseline. You can't just say it equals 0. You have to say it equals 0 and then offer some evidence or some description. It doesn't have to be long. I'm saying it's equal to 0 because that's my baseline. WNCUGA, nothing else equals 0 here. So it doesn't get a whole lot simpler. But I'm going to solve for KB, isolate KB, because my velocity lives in KB. So KB, I guess I don't have to isolate it, equals KA plus UGA plus the work. And I'm going to, instead of calling it non-conservative work, I'll just say it's the work due to kinetic friction. Number 9, KB equals KA, which according to my problem statement is 1/2 mv squared, 1/2 mva. Subscripts are very important, plus UGA, which is MGHA. So I better indicate this is HA right here. This is HA. Plus friction, which I have sitting there. All right, so now with numbers. With actual numbers, I have the kinetic energy at B is 1/2 times 262 over 9.8 times VA squared, which is 0.318. 0.318 meters per second. I got to square that plus M is again, M is going to be 262 over 9.8 kilograms. MG HA. What's HA? Well, some trig. If I look at sine of 36 degrees equals side opposite, which is HA, over hypotenuse, which is 6. So I can make this substitution. HA equals 6 sine 36. 6 sine 36 degrees. So that is whatever it is, 1/2. Oh, plus the work done by friction, which is this for me. This was I should have this in my calculator memory, but this is plus that minus 190.7. Should have that in my calculator, but there it is. And then you're done. That's your kinetic energy at B. And remember, kinetic energy at B is just 1/2 mvb squared. And that means the following. The velocity of the child at the bottom of the slide is going to equal 2 times that kinetic energy, which is sitting there from step 10. This is, again, the kinetic energy at B, all over M, and then just take the square root of that. So let's see what that yields. $7.41307. Okay. That's the velocity of the child at the bottom of the slide. That's the answer to part B. Keep working on this. Take your time. I'll set up one last quiz, I guess. Leave that there. All right. Let's see how everyone's doing on chapter 8, quiz 4. Chapter 8, quiz 4. Pretty good. Some people still are, my guess is, focusing on calculator challenges. But again, I'll add some stoppage time at the end of the match. I will add back some stoppage time. So not to worry. Let's get the official start to the last quiz of today. Chapter 8, quiz 5. It's another ramp problem. So we're probably getting pretty comfortable. I hope the goal is to get comfortable with all of these problems, including ramp. Ramps are common problems. It's a cookie jar. It's a cookie jar moving up an incline. So picture time. Here is an incline looking like, I guess I'll draw it over here. Here's an incline. There's an incline. It makes an angle of 39 degrees. So let's indicate 39 degrees. That's 39 degrees. Cookie jar. And it says at a point 57 centimeters from the bottom. So here's my cookie jar. My cookie jar is sitting right here. Not at the bottom, at that point. At a point 57 centimeters from the bottom of the incline. So I'm going to just indicate that as this. For this point from here to here is 57 centimeters. And I just instinctively go to meters. All right, so that's where my cookie jar is. At this point, it has a speed. At this moment, it has a speed of 2.1 meters per second. So I think I'm just going to call this, I'm going to come right out and say this is energy state A right now. That's energy state A. And at this particular position, moment, the velocity at energy state A is given for me as 2.1 meters per second. Okay, at energy state A, which is right here. Okay, so let's keep going. We have friction. So friction has reared its ugly head. How much farther up the incline will the jar move? So the jar is going to move farther up this ramp. So let's indicate that this is the amount of displacement. So my jar could move up the ramp some distance. That's what I guess I got to find. And then skid to a halt right here. Try that again. Okay. I better call this X. So this is going to be my displacement vector X. There. This is energy state B. Seems to be, again, it's usually kind of intuitive where to label your energy states. And if you're not sure, just label a bunch of them. And maybe you end up not using some of them, but better too many than not enough. All right, so let me just fix this a tad bit. Perfect. All right, good enough, I should say. All right, how much farther does it go? Well, if it's going to skid to a stop, I know that the velocity at B is going to equal to 0 meters per second because it goes as high up as it can go. And what do I need to find? How much farther up the incline? I need to find this X. So my dollar sign is the magnitude of that displacement vector. I'm going to draw it like that. The magnitude of vector X, I can write it like that, or I can write it like this. And that is my dollar sign. Okay. So let's do energy analysis. Number 2, EA plus WNC equals EB. And let's peel apart this onion. At state A, I have some kinetic energy, some gravitational potential energy. There's going to be some non-conservative work. There's going to be some friction stealing energy between A and B. And at B, I have kinetic energy, which I know is equal to 0, and UGB. So low-hanging fruit says there are some zeros here. Oh, I got to establish my baseline. Here's my baseline. Interesting. This will be my baseline right here. Baseline. So with that as my baseline, I have a few zeros here. My kinetic energy at B is 0 because it skids to a stop. My potential energy at A is 0 because that's my baseline. And I guess that's it. Right. So let's keep going. Number 5. Here's my, I'm still not seeing the dollar sign. It's in there somewhere. Here's my kinetic energy at A, 1/2 mVA squared. Plus friction. Here's how I'm going to deal with friction. Here's friction. Ready? It's F sub K times X cosine of theta, where theta is the angle between this vector and this vector, which begs the question, what are my forces? So I'm going to add my forces to my free body diagram. This is normal force. Maybe I better change colors. This is the normal force. This is the weight force. This is friction. Friction always opposes velocity. So I'm going to label those. This is my normal force. This is my weight force. And this is my friction force. And these are vectors. And you can see this angle is 180 degrees. So this is 180 degrees. Okay, and that's theta. And do I need to know any? I need to component. I need to break this up into components. So this is the Y component. This is the X component. It's business as usual. Very familiar now. Don't even have to say much in terms of background story because I think we're past that. But always willing to talk. Okay. What's my coordinate system looking like? I'm going to just call this plus X. I don't know if I'm accelerating up the ramp or down the ramp. I just know I'm accelerating parallel or anti-parallel to the ramp. So that's why this gets called Y and that gets called X. All right, so number 6, step 6. Steps, I wasn't done with step 5. Equals MGHB. Okay. So this was my kinetic energy at A. This was my work done by friction. This is my gravitational potential energy at B. It's all in there. I dropped the zeros. Number 6 then becomes number 6. 1/2 MVA squared. And I know all of that numbered. Well, I don't know mass. I'm not going to worry about that right now, but plus integral of mu sub K times, and I'm going to fast track it a little bit. mu sub k times f sub n, and f sub n is mg cosine of 39 degrees times dx cosine of 180 degrees. And I need to change this from x to dx. This needs to be a variable of integration. So that is dx equals mg hb. So let me just make sure I'm correct here. This is Fn. Because a Y-force inventory shows that this Fn is equal to this component. If this is 39 degrees, that's 39. So I'll let you verify all of that, but feeling good about that being Fn. This is F sub K. And then this is dx, cosine of the angle between them. That's how we get negative work. And then let's do a little quick sidebar on H subscript B. If I look, HB, here's HB right here. HB. So here's the triangle I'm looking at. I am looking at this triangle. That's my hypotenuse. There is my hypotenuse. This is HB. This is the base of that. So I'm just drawing this triangle to make it really easy to see what H sub B equals. This is still going to be my 39 degree angle. So I can see that pretty easily. That's 39 degrees. This is X right here. That's X. All right. So if I do trigonometry, I'm going to say sine of that 39 degree angle equals side opposite over hypotenuse. And that hypotenuse is X. That's my dollar sign. I don't know what it is. So H subscript B, that height at B equals X sine 39 degrees. Okay. All right. Let's just update this. I think could this be the last statement? 1/2 mVA squared cosine of 180 is negative. So there's negative mu sub k mg cos 39 degrees times x. And I'm going to go from, I got to go from 0 to x. So this is going to stay x equals mg hb, and b is x sine. So this suddenly looks pretty complicated. I got a sanity check. This is my kinetic energy at A. Yes. This is mu sub k comes to the left of the integrand. So does m. So does g. So does cosine of 39. All of that comes out of the integrand, and I'm left with, and so does cosine of 180. So the question is, what's the integral of dx from 0 to some x value? And I'm just going to call that x. Okay, I probably should call it dr, but anyway, I think this is good. Mu sub k mg cos 39. All right. Solve for x. Number 8. Solve for x. Do I know everything here? No, I don't know. I don't know the mass, but low-hanging fruit. Mass here cancels with mass here, cancels with mass here. So now it actually got a little more simple. I have 1/2 VA squared minus mu sub k g cos 39 times x equals gx sine 39. Solve for x. That's the distance this cookie jar travels up the plane. 0.5 times. I get this answer in terms of meters, 0.2954 and some change, but they want the answer in centimeters. So convert from meters to centimeters, 29.54 centimeters. That is the answer to part A. That's the answer to part A. Part B, and then we're next. Part C is kind of a no-brainer. What's the time doing? I know we only took one break, so this is kind of a marathon session, but we should be done, I think, within 10 minutes. I think. So we know where it stops. Now the question is, it falls back down. When it falls back down, what is the speed when it hits rock bottom again? So let's just do another drawing because things are getting just a little bit too cluttered. All right, so I'm going to draw the ramp again. It's the same ramp. Okay, so here's my cookie jar way up here, and I know exactly what that location is. And then the question is, now that it's stopped, it's going to fall back down. What is the speed when it hits the bottom? So I might make quick work of this because this is pretty, I think, pretty straightforward. Energy state A, energy state B. So let's just go with that. Energy analysis. Number one, energy at A plus non-conservative work equals energy at B. Let's peel apart this layer. At A, kinetic energy plus gravitational potential energy plus, I'm just going to do this, F sub K dx cos theta equals kinetic energy at B. There's my dollar sign lives there, plus UGB. Better add a baseline here. Here's my baseline. So this is, I think, pretty straightforward at this point. But let's not cut corners. Number three, kinetic energy at A is 0 because it starts from rest. Remember, this cookie jar traveled up the ramp, skidded to a stop. So it starts from rest as it begins its fall back down towards the bottom of the ramp. UGA, I do have to worry about. Anything else? Oh, this is equal to 0. So here's my new and improved EAM. I'm going to give myself some more room here. Step 3. Here goes. MGHA plus, and then here's business as usual. Ready? Coefficient of the kinetic friction force is mu sub K times F sub N. Here's F sub N, mg cos theta. So what I have there in the integrand, actually, it's cosine of 39 degrees. All right, I just wrote down F sub K times dx cosine of 180 degrees. That's all. We're used to that. Equals 1/2 mVb squared. And there's my dollar sign. VB is my dollar sign. All right. You can see the M's cancel. Let's get rid of them. M appears in every term. So here you go. Number 4. GHA. All right. So let's talk about HA. This is probably the only somewhat time-consuming step of this entire problem, this part. All right, so there's my, here's my triangle. This is 39 degrees. That's 39 degrees. There's HA right here. And I remember this point from here to here, this was for me, this was 0.57. 0.57 meters, refer to this drawing here. And then this was X, which I now have, I know what X is. I just solved it. Probably should put that in my calculator memory. Okay, this is X. Okay, so if I do trig here, sine of 39 degrees, sine of 39 degrees equals side opposite HA all over 0.57 plus point, for me, my number was 0.2954. And I'm going to just recall that from calculator memory. So there's where this is where I can say H sub A is, I'll just do this right now, 0.57 plus 0.57 equals 0.865, 0.8654, and some change. I'm just going to keep that in my calculator, meters times sine of 39. And in fact, what I'm just going to do times sine of 39 store alpha B. You can just go right into memory location, calculator memory B, not to be confused with energy state B. All right, so here you go. Step 4. G times H sub A. And H sub A is just sitting there in my calculator memory location B. Plus cosine of 180, you're going to get that negative mu sub K G cosine 39 degrees. And this will be from 0 to yeah, I'll do a little sidebar here. X plus 0.57 equals 0.865 for me. So I'm calculating this distance right here. This is the displacement. This is my displacement vector. All the way from A down, all the way from A down to B. Okay, so this orange vector, maybe I'll redo it over here. This orange vector distance, this displacement this is where I'm getting, it's 0.57, 0.57 plus that X value, which that was the solution to part A. So I'm going to just have this in memory location C. Okay. Point 0.57 plus 0.2954 and some change. Store alpha C. All right, so this will be cosine 39 times the displacement sitting there in my memory equals 1/2 VB squared. Solve for VB. Okay. Pretty involved. 9.8 times alpha B minus 0.17 times 9.8 times cosine of 39 times alpha C times 2 square root 2.9 and some change. That's the answer to part B. This is the answer to part B. This was the answer to part A. part C. Do the answers to A and B increase, decrease, or remain the same if we decrease the coefficient of kinetic friction, but do not change anything else? Decrease, huh? So if I let's see here, number 6. If mu sub k decreases, if mu sub k gets smaller, so if things get slippery, well, I think you can see that if things are more slippery, if there's less friction, then you can kind of know if there's less friction, X increases, the cookie jar is going to go further up the incline because things are slipperier. And by the same token, when it hits the bottom, VB is going to be larger as well. Because if mu sub k decreases, friction steals less energy. So that's why the answer to part C is everything increases. All right, so this was some heavy lifting. And it's now, we get to quit early. It's only 4:12. It seems like a crime to stop so early. But on the other hand, we only took one 10-minute break. Well, 15 minutes because I was late. That's it for me, you guys. So do you have any other questions or comments or requests of me? Put this back up on the screen and I will bow out and you guys can work. I think this is open for a pretty long time. So you shouldn't run out of time. I'm going to go run off and take care of a little bit of business and come back, but I'll leave this up and running. And then we'll see you guys on Thursday.